Episode 33, titled Distance and Similarity Metrics, Euclidean, Manhattan, Cosine, and When to Use, the goal is to choose distance measures that match your data geometry, because DataX questions often hide the right metric choice inside the meaning of close. Distance is not one universal concept. It is a definition you choose, and that definition determines what your model or method considers similar, which in turn shapes clustering, retrieval, and nearest neighbor behavior. When you select the wrong metric, you can get results that look mathematically valid but are semantically wrong, meaning the system groups or retrieves items in ways that do not match the problem. The exam rewards you when you can infer the geometry implied by the data, such as whether magnitude matters, whether direction matters, and whether features are comparable in scale. This episode will cover Euclidean distance, Manhattan distance, and cosine similarity in practical terms, then connect those choices to normalization, mixed data types, high-dimensional effects, and algorithm behavior. The point is to make metric selection feel like a decision about meaning, not a memorization exercise. When you can explain why a metric fits a dataset structure and goal, you will consistently pick the best answer. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Euclidean distance is the straight-line distance you already know from geometry, and it is most appropriate when features are on comparable scales and when magnitude differences should count directly. If you represent each record as a point in feature space, Euclidean distance measures the shortest path between 2 points, which aligns with intuition when the axes are commensurate and the units are compatible. This works well when features are normalized or inherently comparable, such as standardized numeric measurements, and when changes in any dimension should contribute smoothly to overall distance. The exam may describe physical-like measurements or standardized scores, and Euclidean distance is often the right default in those contexts. However, Euclidean distance is sensitive to scale, meaning a feature measured in large units can dominate the distance even if it is not the most meaningful feature. That is why the exam often pairs Euclidean distance with a cue about scaling or normalization, because without scaling, Euclidean can encode the wrong idea of similarity. DataX rewards choosing Euclidean when straight-line geometry fits the meaning of closeness and when scaling is controlled. Manhattan distance, also called city block distance, measures distance as the sum of absolute differences across dimensions, which aligns with grid-like movement and often behaves more robustly in certain high-dimensional settings. Instead of imagining a straight-line path through space, you imagine moving along axis-aligned steps, like navigating a city street grid, which makes Manhattan distance sensitive to differences in each feature in a linear, additive way. This can be helpful when you want a metric that is less sensitive to large, single-feature deviations than Euclidean, because Euclidean squares differences and can amplify outliers in one dimension. Manhattan distance can also be a good fit when the domain naturally involves step-like changes, such as counts, or when interpretability favors thinking in terms of total absolute change rather than straight-line deviation. The exam may describe a preference for robustness or for additive distance contributions, and Manhattan distance often fits that cue. It is not a cure for all high-dimensional issues, but it is frequently considered when Euclidean becomes overly influenced by large deviations or when the geometry of the problem is more grid-like. DataX rewards selecting Manhattan when the notion of closeness is better expressed as summed steps than as straight-line magnitude. Cosine similarity is different because it focuses on direction rather than length, measuring how aligned two vectors are rather than how far apart they are in magnitude. This makes it especially useful for text embeddings and sparse representations, where magnitude can reflect document length or overall frequency rather than content similarity. In cosine similarity, two vectors are considered similar if they point in the same direction, meaning they share a similar pattern of feature weights, even if one is larger overall. The exam often signals this with phrases like embedding, text similarity, or compare patterns independent of scale, and those are strong cosine cues. Cosine similarity is also useful in recommendation and retrieval contexts where you care about relative preference patterns rather than absolute volume. The key is that cosine similarity treats scaling as irrelevant, which is exactly what you want when scale differences are artifacts rather than meaning. DataX rewards this choice because it demonstrates that you understand similarity as angle in some domains, not distance in the everyday sense. Scaling changes distances, which is one of the most important practical insights the exam expects you to carry into metric selection. If one feature has a large numeric range and another has a small range, Euclidean and Manhattan distances will be dominated by the large range feature unless you normalize or standardize. This means two records can appear far apart due to a feature that is numerically large but semantically unimportant, and that produces misleading clustering and nearest neighbor results. Normalization, such as scaling features to comparable ranges or standardizing to similar variants, is a common mitigation because it makes each feature's contribution more balanced. Cosine similarity implicitly normalizes by vector length, but it still depends on the relative feature weights, so pre-processing choices still matter. The exam often tests this by describing unscaled features or mixed units and asking what should be done before applying a distance-based method, and normalization is usually the correct action. DataX rewards this because it reflects real-world workflow discipline. You match metric choice and pre-processing to the meaning of features, not just to convenience. Mixed data types add complexity because not every feature behaves like a numeric measurement where Euclidean or Manhattan distance makes direct sense. Categorical variables, ordinal variables, and binary flags can require different handling, such as encoding strategies that preserve meaning without creating artificial distances. The exam may describe a dataset with both numeric and categorical features and ask how to handle similarity, and the correct answer often involves choosing a metric strategy that respects different feature types rather than forcing everything into one naive numeric space. This can include using appropriate encodings, weighting feature contributions, or choosing specialized distance measures designed for mixed types. The key is to avoid pretending that a category label is a continuous number, because that creates distances that reflect arbitrary coding rather than real similarity. DataX rewards this because it shows you understand that distance depends on representation, and representation must preserve semantics. When you can say that mixed types require a metric strategy, not a single naive formula, you are reasoning at the level the exam expects. The choice of metric can differ depending on whether you are clustering or doing nearest neighbor retrieval, because those tasks have different sensitivities and different interpretations of similarity. Clustering often focuses on group structure and can be influenced heavily by global geometry, meaning the metric choice shapes the clusters you discover and how stable they are. Nearest neighbor retrieval focuses on local neighborhoods, meaning the metric determines which points are considered most similar to a query and therefore affects results directly and immediately. The exam may describe grouping customers into segments versus retrieving the most similar past case, and those are different goals that can guide the metric choice. For clustering with standardized numeric data, Euclidean is common, while for sparse, text-like data, cosine similarity is often more appropriate. For nearest neighbor in high-dimensional numeric spaces, Manhattan can sometimes provide a more robust notion of difference depending on the distribution and scaling. DataX rewards recognizing task context because it ties metric choice to what the method is being used to accomplish. A common exam warning is to avoid Euclidean distance on sparse text counts without proper normalization because raw count vectors are dominated by document length and frequency rather than by content pattern. If you compare two documents using Euclidean distance on raw counts, longer documents often appear farther from everything, not because they are semantically different, but because they have larger magnitude across many dimensions. Cosine similarity avoids that by focusing on direction, which corresponds more closely to word distribution patterns. Normalization can also help, but cosine is the most common and natural choice in this domain because it aligns with how embeddings are interpreted. The exam may describe bag-of-words representations, sparse vectors, or embedding-like features, and the correct answer often cautions against Euclidean without normalization. This is one of those places where the exam rewards a very practical modeling instinct that many learners only gain through experience. When you recognize that sparsity and magnitude artifacts distort Euclidean, you will choose the more defensible metric. High-dimensional geometry introduces the curse of dimensionality, which reduces distance contrast and makes many points appear similarly distant, complicating nearest neighbor and clustering methods. As dimensionality increases, the distribution of distances can become concentrated, meaning the difference between the nearest and farthest neighbors shrinks relative to the overall scale. This reduces the usefulness of distance for discrimination because nearest becomes less meaningful when everything is about equally far. The exam may describe poor nearest neighbor performance in high dimensions or unstable clustering, and the correct reasoning often includes acknowledging the curse of dimensionality and considering dimensionality reduction, feature selection, or alternative similarity representations. Manhattan distance can sometimes behave differently than Euclidean in high dimensions, but the broader issue is that high dimensionality itself makes distance-based discrimination harder. DataX rewards understanding this because it explains why methods that work well in low dimensions can struggle in modern high-dimensional feature spaces. When you recognize distance concentration, you can choose answers that suggest reducing dimensionality or adjusting representation rather than blindly changing metrics. Distance intuition also helps you understand how k-means and k-nearest neighbors behave, because both methods are built on a notion of closeness. K-means clustering, often shortened as k-means once you have said k-means, typically uses Euclidean distance to assign points to the nearest cluster center and to update centers as means, which makes Euclidean geometry central to its behavior. K-nearest neighbors, often shortened as KNN, after you have said KNN the first time, relies on a distance metric to decide which training points are closest to a new point, and the chosen metric directly determines which neighbors are selected. This is why scaling and metric choice can dramatically change results. Change the metric, and you change the neighborhoods and clusters. The exam may ask what influences k-means clustering or KNN retrieval, and metric choice is often a key part of the answer. It may also test whether you recognize that k-means assumes a geometry that makes means meaningful, which is a Euclidean-friendly assumption. DataX rewards this because it shows you understand that algorithms are not independent of the metric. The metric defines their notion of structure. Metric choice also involves domain constraints like interpretability and computation cost, because the best metric is not only mathematically plausible, but operationally feasible and explainable. Euclidean distance is easy to compute and easy to explain as straight-line difference, which can be valuable when stakeholders need intuition. Manhattan distance can be explained as total absolute change across features, which is also interpretable and can sometimes align with business notions of difference. Cosine similarity can be explained as similarity in pattern, which can be intuitive in text and embedding contexts, but can require more explanation for non-technical audiences. Computation cost matters because distance calculations can be expensive at scale, especially in large datasets with high dimensionality, and some metrics may be more efficient or more amenable to indexing strategies. The exam may describe constraints like performance requirements or limited compute, and the best answer may involve choosing a metric that balances fidelity with feasibility. DataX rewards this because it treats method choice as a system design decision, not just a math choice. When you consider interpretability and cost alongside geometry, your answers become more realistic.
Communicating metric choice should be framed as matching the meaning of closeness, because the exam often rewards explanations that tie metric selection to what similarity represents in the domain.
If closeness means similar magnitude across comparable features, Euclidean can be appropriate after scaling. If closeness means similar total deviation across features in an additive sense, Manhattan can be appropriate and can be robust to certain outlier behaviors. If closeness means similar direction in a feature space, such as similar word usage patterns or embedding alignment, cosine similarity is the natural choice. This style of communication avoids arguing that one metric is universally superior and instead shows that you chose the metric because it matches the decision question. DataX rewards this because it reflects professional reasoning. You define what similarity means, then choose the metric that encodes that meaning. When you can explain similarity in domain terms, you can justify your selection cleanly under exam conditions. A useful anchor for this episode is that Euclidean is length, Manhattan is steps, and cosine is angle and direction, because it keeps the geometry straight under pressure. Euclidean corresponds to straight line length in feature space, which fits when magnitudes matter and features are scaled comparably. Manhattan corresponds to the total step distance across dimensions, which fits when additive differences and robustness are important. Cosine corresponds to the angle between vectors, meaning pattern alignment independent of scale, which fits text and embedding similarity. This anchor also helps you remember when normalization is needed, because Euclidean and Manhattan are scale-sensitive, while cosine is primarily direction-focused. Under exam pressure, the anchor provides a fast mapping from problem type to metric type without requiring you to recall formulas. DataX rewards this because it increases speed and reduces common mistakes, especially in sparse and high-dimensional contexts. To conclude episode 33, pick one dataset and justify a metric selection, because that is exactly what the exam is testing when it asks you to choose a distance measure. Choose a dataset like standardized numeric measurements for clustering, sparse text embeddings for retrieval, or high-dimensional behavioral features for nearest neighbor, and state what closeness means in that domain. Then select Euclidean, Manhattan, or cosine accordingly, and include the key pre-processing step, such as normalization, when scale differences would distort distance. Mention the high-dimensional caution that distance contrast can shrink, and that representation choices may matter more than the metric itself when dimensionality is high. Finally, Tie your selection to interpretability and computation if the scenario implies operational constraints, because metric choice must fit both meaning and feasibility. If you can narrate that justification clearly, you will handle DataX metric questions with calm, correct, and defensible reasoning. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.